Hello and welcome. This is going to be our lecture video for April 29th. Just going to do a few more trig problems today and then just sort of talk about how these problems connect to the real world. So the goal is to review solving equations with trig functions, connect these types of problems to the real world. While we're doing this, much of the physical phenomena that we interact with on a daily basis are waves, including light and sound. So being able to work with sine and cosine can be very helpful in a physics class or to understand something like tides. All right, but we're starting with just some of the pure math problems. Got one right here. Hopefully you've got your notes out. Today's date at the top. Go ahead and copy this one down. How are we going to solve it? Well, first thing, we want to isolate this trig function. Ideally, we want it to be trig function equals a fraction, and then we can go to our unit circle. So we got to get rid of this 1/2. So what am I going to do? I'm going to multiply both sides by 2 because a 2 gets rid of a 1/2. All right, so this is going to become negative 2 root 2 over 4 equals cosine of theta. Can this be simplified at all? It can. We can cancel out that 2 and turn this 4 into a 2. And now we have negative root 2 over 2 equals cosine of theta. Excuse me. All right, so we're trying to figure out some angle in our coordinate plane where the adjacent over hypotenuse is equal to negative root 2 over 2, because that's what cosine stands for. So I'm going to label the top of this adjacent and the bottom of this hypotenuse. All right, so I go to my coordinate plane. The adjacent, when I draw a triangle in here, let me draw all of my possible triangles. The adjacent is that bottom length. So I have to be dealing with these two triangles over here. All right, where the adjacent will be negative. So let me get rid of these two. And I can label this negative root 2. Now the hypotenuse is 2, so it can either come out like this and be 2 or come down like this and be 2. And this should be familiar as our 45, 45, 90. So that interior angle is 45, meaning out here is 135 or 3 pi over 4 or 5 pi over 4. Now to get all of our answers, we have to add multiples of 2 pi to both of these, because I can get to that same terminal side by doing 2 full rotations and then doing an additional 3 pi over 4, or 10 rotations and then doing 3 pi over 4. So what I do is I say 3 pi over 4 plus 2 pi n. And it's just always plus 2 pi n with sine and cosine, and then plus pi n with tangent. And then we'll say plus 2 pi n, and then somewhere we need to say what n is. And as long as you write it one place in your paper, it counts for the whole paper. N is an element of the integer, so it is any integer. That's how we get multiples of 2 pi. Okay, so that's we're going to change gears a little bit and look at one with operations inside the argument of the trig function. The first steps are still the same. We got to isolate this trig function, so we want to add 2 to both sides. Plus 2, but 2 is the same as 4 over 2, and if I write it as 4 over 2, then I can just combine these directly. So these cancel out, and I've got cosine negative 3 theta plus pi. Oh, tablet just died. Gonna replace that. All right, equals, add just the top, so we get negative 1/2. So at this point, we do our labeling of adjacent over hypotenuse, because we're dealing with cosine. If it was sine, it would be opposite over hypotenuse. If it was tangent, it would be opposite over adjacent. We've got to draw this into our coordinate plane. So I'll do that up here. When the adjacent's negative, we come over into these two quadrants. Adjacent's negative 1, hypotenuse is 2, and this should look familiar as our 1, 2, and the square root of 3 triangle. which is our 30, 60, 90. Right in here is the 60. So that makes this 2 pi over 3 and 4 pi over 3. You'll start realizing when solving these problems, although like the steps are kind of confusing, there's really not a great variety of answers. You know, certain answers are always paired up with other answers. There's only so many ways we can draw triangles in here using our special triangles, which these problems try and do. So just keep that in mind. All right, so here we've got, now it's negative 3 theta plus pi equals 2 pi over 3. Let's do a big over 3 plus 2 pi n. N is an element of the integers again. And then I'll write it off to the side here. Same thing, negative 3 theta plus pi equals 4 pi over 3 plus 2 pi n. And now just solve for theta. So I can subtract pi from both sides. I want to subtract it from this term, not the term at the end. That gets kind of tricky because we don't know what the coefficient is since we don't know what n is. So now I've got negative 3 theta equals negative pi over 3 plus 2 pi n. I'll just finish on this side. Got divide by negative 3, divide by negative 3, divide by negative 3. And I get theta equals pi over 9 plus 2 pi over negative 3 n, or maybe you want to move the minus out here. Actually, I like it with the plus there, and then negative 3. Yeah, and if you don't want this to be negative, you can actually just add multiples of this to itself because n is any integer. So you just like move it up 1. Don't worry about that if that confuses you, but just in case it doesn't exactly match, that might be what happened. All right, let's do this one over here. Subtract pi from both sides. Negative 3 pi equals pi over 3 plus 2 pi n. Excuse me. Divide everything by negative 3. And we get theta equals negative pi over 9 plus 2 pi over negative 3n. Okay, and that whole thing is our answer plus somewhere we have to define what n is. Okay, last one, just to verify. Watch out for these verify. Now that we've started solving, these ones feel like you have to solve them, but if you see that word verify, it's an easier problem. We just have to get the two sides to match. All right, 1 over cosecant squared minus 1 equals sine tangent secant. All right, so I'm going to turn everything into sines and cosines. So the cosecant squared, that's going to become 1 over sine squared. So this is going to become 1 over sine squared minus 1. Reminder, I like to drop the x's when I'm doing verifications just to save a little bit of writing. And you got to write what we did. We just did a reciprocal identity there. Equals sine times sine over cosine times 1 over cosine. I just used a quotient identity or a tangent identity. It means the same thing. And another reciprocal identity. Okay, can anything cancel over here? No, but we can combine this to be a sine squared over cosine squared. So this here becomes a sine squared over cosine squared. I could turn that back into a tangent squared, but I can probably actually match this easier. So I'm going to turn this 1 here into a sine over sine, or a sine squared over sine squared. So now I've got 1 over 1 minus, or 1 over sine squared minus sine squared over sine squared. This becomes 1 over 1 minus sine squared all over sine squared. Still equals that. Off to the side, I'm going to write my Pythagorean identity. Sine squared plus cosine squared equals 1. I'm going to change it to look like this by subtracting sine squared from both sides. And then I get cosine squared equals 1 minus sine squared. So 1 minus sine squared can be replaced with the cosine squared. Maybe now you see how this is going to work out. So 1 over cosine squared over sine squared. And then I copy dot flop. Copy dot flop, and then I get sine squared over cosine squared equals sine squared over cosine squared. I've got the two sides to balance. Let's go back up to the original one and figure out domain of validity. So cosecant, that is hypotenuse over opposite. Sine is opposite over hypotenuse. Tangent, opposite over adjacent. Secant, hypotenuse over adjacent. And I say I've got both opposites and adjacents in denominators, so I have to say that x cannot equal n pi over 2. Again, n is an element of the integers. It works for these problems too. Okay, and that's a verification problem. They're not super satisfying unless you consider getting the two sides to match to be satisfying. It's not like we solve for x and then this domain of validity thing can be kind of annoying, but there's only 3 ways it can work out, so you just have to memorize those. We're going to talk about real world applications here. I don't have any problems to go along with them. I just want to talk about sort of why is it important to be able to solve an equation with 2 sine waves. All right, so there's a lot of times in life where 2 waves are going to interact. For this page, think about shining 2 laser beams out of the same laser pointer. So what can happen with 2 waves is if they are in phase with each other, then the peak of one wave gets to add on top of the peak of the second wave, and you get this taller wave. But destructive interference is where they're out of phase. So same amplitude, same period, but phase shifts by half of a period. And then the peak of one matches with the trough of another, and they totally cancel out, and you get nothing. You get this just blank line. So one way we see this happening, one way destructive interference is really useful to us, is with noise canceling headphones. So now imagine that these are sound waves, and if you put a speaker in between your ear and the source of some sound, that speaker can match the sound and then just phase shift it slightly and get this destructive interference to happen right at your eardrum. All right. Another time when sine waves are added together would be with the tides. The tides are not a perfect sine wave, and that's because it's more than just the moon acting on the water. The sun's gravitational pull also can pull a bulge of water to the front of Earth, and then the physics works out that you get another bulge on the opposite side of the Earth. When you pull water to one side, it also gets pulled to the other side. I don't exactly understand why that works out, but it just does. Something to do with, I think, the Earth spinning or something. But if the moon and the sun are lined up, you'll get an extra high tide. And if they're not lined up, the moon actually has the stronger gravitational pull because of how close it is. So you'll get a high tide, but it'll be less strong. And then these effects are compounded by the fact that the Earth and the moon have elliptical orbits around the sun and the Earth respectively. And so that means when you're at the closest point of that ellipses, what's called the perihelion, the effect is stronger, and when you are at the furthest point, the effect is weaker, the aphelion. I think I'm saying this right. At least that's when it's with regard to the sun. That's what the helion, I think, refers to. When it's around the Earth, it's perigee and apogee. So you can get a really, really strong tide if you can line up the sun and the moon and have the Earth and the Moon both be at perigee, you can get a really strong tide. And another thing that affects tides is your latitude. So the further towards the pole you are, the more regular the tides will be. And we can see this first graph up here. This is for Boston, Massachusetts. We can see the tides are going up and down. And then the stronger tides are called spring tides, and then the weaker tides are called neap tides. But we can see in San Francisco, California, this gets kind of really mixed up. There's lots of other things affecting it. Here we are at Galveston, Texas. Very different tide pattern. Pakhoi, China. This type of tide pattern is called diurnal, and this one up here is semi-diurnal, and then these ones in the middle are mixed. So, my whole point here is just that just knowing how to draw one sine wave might not be enough to describe physical phenomenon. You might need to be able to combine sine waves to really show what's going on. Let's talk about what sound waves actually look like. For one, they aren't waves that go up and down. They are waves of rarefaction and compression. I think it's called a longitudinal wave. Things aren't moving up and down like on the surface of the ocean. They're compressing and expanding, like think of a slinky and sending a wave along that. And when you have two speakers, you can get that constructive interference and destructive interference that we talked about with the Bose headphones, but it happens at nodes, which are specific spots in space. Another place we see this is in microwaves. You can get nodes, standing waves in the microwave of that electromagnetic radiation, which will heat up certain spots more than others. And that's just based off of how it's bouncing around in the microwave. You'll get a spot that gets really hot, a spot that doesn't get really hot, and it's because of constructive and destructive interference. Okay, there's a worksheet linked on today's class with a bunch more just algebra-based problems. It's not collected, but I think you should do as many as are needed to feel comfortable solving these types of problems. All right, I'm going to make a video for that one now, so I'll see you guys over there.